Hi again, it's Dennis Gravert with more organic chemistry. We're going to change gears today. We're not going to be talking about naming molecules or looking at different isomers, looking at a bunch of different organic molecules or functional groups. Instead, we're going to look at shapes of molecules. We're going to get a little more subtle, a little more detail oriented. So we're in Key Concepts Unit 1, Part 4. And this is all about conformational analysis. Sounds pretty scientific, conformational analysis. All that is we're analyzing shapes of molecules. Okay. So to get started, we just have to realize that single bonds usually allow for free rotation. And we're not looking at different molecules when we bend them or twist them, right? So over here on the right, trick question, which one of these is butane? Written over here on the right hand side. Yeah, they're both butane, right? 4 carbons in a row, non-branch, a saturated hydrocarbon, all single bonds, C4H10. Yeah, but whether you have the chain kind of bent like a letter C lying on its side, or you have a zigzag structure, 4 carbons sequentially attached. Yeah, this is a drawing of two different shapes of butane. And what's happening here is this middle single bond is allowed to rotate. Kind of draw a rotational arrow here. That looks horrible. Let me see if I can do a better one down here. Yeah, kind of rotate that bond, spin it, and we can get this last methyl group to be up on top or down below. And it turns out that some shapes, some conformations, there's a scientific term for shapes, conformations. Some conformations are more stable than others. So let me ask you this, of these two shapes for butane, which one do you think is more stable? Which one do you think nature prefers? Turns out it's the bottom one. If you expand all the bonds, show all the bonds, and actually draw it accurately, get the bond angles and the bond lengths correctly, you'll discover that when butane is in this crescent C shape, that's an awkward name for the shape. We got a better name coming up. These two hydrogens over here are getting pretty close. And it's not the protons that are necessarily getting close, it's the bonding electrons, right? Bonding electrons are on those orbitals. The 1s orbital overlapping with the sp3 orbital here, they're kind of out in space, and the bonding electrons from this side, the right side, are getting pretty close to the bonding electrons on the left side. Electrons don't have to touch or collide in order to feel each other. They're electrostatically repelling each other. Like charges repel. And so butane doesn't like to get in this shape because these bonding electrons are getting too crowded. They're crowding each other out. Whereas if you get in this other straight chain, but a kind of twist, the methyl group on one end is much farther away from the methyl group over here. The electrons are farther apart. You don't get that electrostatic repulsion, and it's a much more stable molecule. So nature prefers this bottom shape. We just did conformational analysis. Hey, just analyzed it. We kind of predicted which shape is more stable based on crowding. Sometimes there's other factors though. Why do we have to do this? Well, it turns out that the shapes of molecules affect the reactivity, how they interact with other reagents, or sometimes just the way they interact with things. Like I got on this page here, biological receptors. Receptors are proteins, really important ones in our body that actually latch on or grab to other molecules. And some of them behave like a lock and key. So the molecule that they're trying to attach to, if it doesn't have the exact shape and right functional groups, functional groups of biology, that's important. If it doesn't have the right shape and functional groups, the atoms, it won't bind, it won't attach. And so they're very selective, and that's actually a key way biological systems operate. And so if you're going to investigate that, you need to know something about shapes of molecules. Okay, so if we're thinking about shapes, we have to be thinking 3-dimensionally. So we need a new tool on how we can analyze shapes, how we can do conformational analysis. And a very good and useful tool is something called Newman Projections. Okay, so what's a Newman projection? Right here in the middle is not a Newman projection, but rather this is the old what is this called? A complete structural formula, if you will. And we're showing three-dimensional shape because we're using the wedge bonds. That looks like a perspective drawing coming out at you. So this methyl group, the CH3 group, and this other hydrogen on this wedge bond, they're coming out of the computer screen towards you. And the atoms, the two H's on the dash bonds, are fading into the distance. They're going away. So if you look at this molecule from the side, so if you can imagine, and I know not everyone can do this, but give it a try. If you can imagine looking on the edge of your computer screen or your phone, however you're viewing this video, if you got to the side, then this methyl group would actually be on your left-hand side, and the hydrogen would be on the right-hand side. And that's what's shown down here. The methyl group is on the left-hand side and the hydrogen's on the right. And as you're looking at this, this hydrogen would be pointing down, and you got the colored hydrogens away from you. These three hydrogens are attached to this carbon right here. And that's what the circle represents. The hydrogen in the, the carbon atom in the back with its three attached hydrogens. And the other perspective is, let's say that you decide to look at this very same molecule in this exact shape, but from the left-hand side. And so now the closer carbon is the one that bears three hydrogens. That's this dot that represents the forward carbon with three attached hydrogens. And from the perspective of this eyeball, this carbon on the right is farther away. It's in the distance, represented by this circle. And from this eyeball here, as you look at this methyl group, it is going to be on the right-hand side from the point of view of the eyeball. So yeah, that's where the methyl group shows up on the right, attached to this circle. And this hydrogen over here is on the left-hand side. We're going to take a step-by-step approach at drawing these Newman projections, but it begins by understanding what are they supposed to be representing. It's the eyeball looking straight down this bond, connecting what I call the dot forward carbon to the back, or the circle carbon. And then how do you inspect different shapes? Well, you get to spin one of these carbons, the dot carbon or the circle carbon, and you can spin the groups and see who's getting crowded, who's colliding, in a sense. And we're going to spin it just like the helm of a ship. Here's Captain Jack Sparrow. And if you know, this is not an exact representation of a Newman projection, because I don't know where your dot and your circle would be. You don't have all 6 bonds bonding together. But the way this spins is kind of reminiscent of a Newman projection. All right, so I might refer to the helm of the wheel and give it a spin or something like that. Oh, this is a good point. There's more than one correct answer, right? So if I draw this, or I might name it. There is a video on how to name organic molecules. Find the longest chain. Well, there's 1 carbon here, 2 carbons there, 3 there. Any double bonds or triple bonds, any other functional groups, halides? Nope. This is just a hydrocarbon. This is an alkane, 3 carbons long. That's propane. Sure. So on the exam, I say, hey, draw for me a Newman projection of propane. And here's 2 correct answers, and there are a lot more. It just depends on your point of view. Okay, how do we draw these Newman projections? Before we draw one, let's get a better 3-dimensional image of, I'm going to try drawing butane. So let's go over here. I found this one website that can allow you to rotate a 3-dimensional model in space. It's kind of cool. I'll put the link in the comment section. So this is kind of cool. I got it zoomed in. Here's butane. And it's in the less stable shape, the less stable conformation. And if I press the play button, there goes that free rotation, full 360. And that's what happens in nature. These single bonds are free to rotate. And not only about this single bond, but every single bond is free to spin. For butane, what makes it most interesting is when this bond between carbon 2 and 3, right? So go back to naming, 1, 2, 3, 4 carbons, and we'll call this carbon 2 and this one carbon 3. So the bond, ooh, that's kind of nice. The bond between carbon 2 and 3 is allowed to spin. If I stop it, I didn't stop it. Try again. There we go. We can stop the rotation here, take a little look, and that's the most stable shape, the most stable conformation for butane. But now what I want to do is I want to draw this. So will I be able to draw this? Okay, so right now, no, that's not what I want to do. Okay, so can't show you two screens at once. So as you look at this, we got one methyl group on the top left, goes down to carbon 2, which is horizontally drawn, and then carbon 3 goes down to carbon 4 down the bottom right. So let's draw that here. Carbon 1, attach the carbon 2, attach the carbon 3, attach the carbon 4. And now let's expand it three-dimensionally. So all of these bonds are in the plane of the screen. Yeah, let's start with this carbon here. This carbon is sp3 hybridized. It's got 4 single bonds. So it must be tetrahedral. Tetrahedral geometry. The bond angle is a 109.5 approximately. So this bond angle here is 109.5. It's sp3 hybridized. And now if I draw another hydrogen, well, maybe it'll come out towards us like this. And then there's going to be another hydrogen beyond us into the screen. And I'm hoping you can kind of visualize that as a tetrahedral shape. Same thing here. Oh, no, we're not. Let's just draw the CH3. We're only going to be particular about carbon 2 to carbon 3. We're worried about its shape. The shape of the molecule about the C2-C3 bond. The hydrogen coming out towards us and another hydrogen fading into the distance. Good, sp3 geometry. Now, get our eyeball over here. Eyelashes, if you will. We're gonna look this way. And as I look towards this carbon, the methyl group's gonna be pointing up. Okay, so we're on the left-hand side of the molecule. We're gonna look down this C2-C3 bond, and the methyl group closest to us is gonna be pointing up. That's the goal. Let's see if we can get the other computer program to do that. Okay, so we're on the left-hand side, and we're gonna rotate this. Yes! And now, this methyl group up here is pointing up. And in the Newman projection, look at carbon 2 versus carbon 3. We want to look straight down that carbon 2, carbon 3 bond. And now we can't see carbon 3. It's hiding behind carbon 2. There it is. Here's carbon 3 back there. Carbon 2 is in the front. And you also can see it's not a full 180 degree here because I didn't stop it right on the mark. Well, that's okay. Maybe it kind of helps. You can see that it's free to rotate. Okay, I want to draw the molecule in this shape with this top methyl group above and this hydrogen up to the bottom left and this hydrogen up to the bottom right. Okay, so how are we going to begin the Newman Well, begin with the bond you're looking down. This carbon in the front is represented by a dot. The carbon in the back, there it is. This carbon in the back is going to be a circle. There. Bounce back to here. Trying to get dizzy from all this moves. Okay, so we'll draw our Newman ray over here. So the forward carbon is a dot. So I'll put a dot here to remind me who's forward. I'll put a circle around this carbon. Yeah, so the Newman has a dot and a circle. And carbon 3 is away from the eyeball. It's hiding behind. Carbon 2, the forward one, the dot. Okay, let's get the rest of the molecule in here. So I've already drawn the forward carbon. The methyl group's pointing up. Hydrogen to the left, hydrogen and down. Down to the left, the other hydrogen down and to the right. Okay, so on the forward carbon, we got the methyl group pointing up. And we have a hydrogen down and to the left, the other hydrogen down and to the right. Cool. Now let's draw the back carbon. Okay, so the back carbon's right here, carbon 3. Rotate it so I'm looking at Newman. And then there's a methyl group. See the methyl group? It's attached to the back carbon, the circle carbon. The methyl group's going down. There's a hydrogen up and to the right, and another hydrogen up and to the left. So that's from the right perspective. So on the back carbon, methyl group down, hydrogen up and to the right, hydrogen up and to the left. Okay, so starting on the back carbon. If you're drawing on the back carbon, begin your bond on the circle. Don't accidentally connect it to the dot, because now you're giving it too many bonds. So the back carbon, let's start right here. Draw a line down, the methyl group is pointing down. On the back carbon, up on to the right, there's a hydrogen. And on the back carbon on the left side, there's another hydrogen. We just drew our first Newman projection. Hooray! And now I'll ask you, what's the orientation of the two largest groups? Well, hydrogen is the smallest element. Carbon's bigger than hydrogen. It has 2 shells of electrons, the 1s electrons, a 2s and a 2p. And the carbon also has 3 attached hydrogens. So this group is bigger than an H. And this group is bigger than H. And these are opposite. Or they're opposite or counter each other. We call it the anti or anti-conformation. Conformation. Cool. Let's go back to our key concepts because we got that definition there. Okay, so we got this all right. Here we go. Oh, I just drew anti-conformation. The 2 largest groups are 180 degrees off each other in a staggered conformation. Ooh. So staggered just means that the groups are alternating. They look like the helm of a wheel, the helm of the ship. And you can see that, hey, this CH3 group is separated, it's staggered with respect to this hydrogen. There's a distance there, and the hydrogen, another one over here, another one here. They're evenly spread out, they're staggered, they're alternating. And the way it alternates is this methyl group's on the forward, So we have group on the forward, then group on the back, group on the forward, group on the back, group on the forward, group on the back, and they're evenly spaced out. This is staggered, a staggered conformation. And it's a special one where the biggest groups are the whole thing is staggered, but the two biggest groups are actually opposite each other, the anti-conformation. Let's get a different shape. Let's move back here. And then we're gonna rotate it. That's probably too far. Let's go back. That's not stopping. There we go. And well, that's not so nice. You can see that things are not evenly staggered. In fact, let's rotate it this way. There we go. This is one of the least favorable conformations, the most crowded. And if this was the, if the moon was the forward one and the sun was the back one, if the moon gets in front of the sun, we say there's a solar eclipse. The sun is being eclipsed by the moon. So this is also called an eclipse conformation. Because not only is the forward carbon hiding or eclipsing the back one, but the forward methyl group is eclipsing the back methyl group. And the hydrogen down into the right is eclipsing the hydrogen down into the right in the back one. You can't even see that one. That's actually really well eclipsed. Yeah, and it turns out this is hard to draw, which makes it a great tool for analyzing structures. So I'll show you how to draw it. But the fact that it's going to be difficult, if not impossible, to draw these back atoms, the other back groups, that tells you at a glance that this is very crowded. And if it's crowded, it's probably not a favorable structure. It's a high energy structure. It takes energy to make the molecule get to this shape where everything is crowding each other out. What's crowding? Yes, this hydrogen is starting to get too close to the electrons of this hydrogen, but the electrons around this hydrogen are actually fairly close to the electrons of this one. You're getting some electronic repulsion between the electrons. All right, let's draw it. If we focus on the forward carbon first, methyl group up, hydrogen down and to the left and right. Down here. So now we got the dot, that's the forward carbon. And we said on the dot there was a methyl group pointing up. Like that. And there's also one pointing down to the left, down and to the right. And then what about the orientation of the groups on the back carbon? The methyl group's also up. Hydrogens are down and to the left and right. And what you can do is you can, instead of drawing the molecule from the point of view where you're supposed to look exactly down the carbon 2-3 bond so you can't see the back one. You can actually pretend to twist the molecule a little cockeyed like I have here, so that the hydrogens in the back and the methyl in the back kind of sneak out from behind. You kind of make, kind of get a glimpse of them. And that's actually a better way of drawing this shape through a Newman projection. So let's draw the back carbon. That's a circle. Ew, ugly circle, try again. It's better. Start on the back one, and then I'm drawing it not exactly on that line, right? I know that'd be really messy. Just a little bit off the side, a little cockeyed, and I'll insert CH3. I'll do the same thing here. Now, you can decide to put the bond just a little bit below, the bond a little bit above, whatever you want, just close. And if you want to make that line longer, shorter, it's okay. Personally, I like making it a little shorter because it looks like it's smaller as it fades into the distance. That's just a personal preference. But there you go. This is more difficult to draw than the staggered conformation. This is an eclipse conformation. Sorry, conform conformation. Cool. Definitely not anti. The two biggest groups are actually crowding each other out. That's not so nice. Let's go back to our key concepts. Let's see what terms are still missing. Which ones still need some definitions? We got staggered and eclipsed. Good. Staggered are more favorable, more stable, less energetic, right? So in order to get the molecule into the eclipse conformations, you're pushing the molecule into a shape where the electrons are starting to repel each other, trying to push apart. But you're like, no, get into the shape. So you have to push against that electronic compulsion. Now in the real world, these molecules, let's say it's butane. Butane is found in cigarette lighters or any of those, well, you know, some lighter that you're gonna light birthday candles with or whatever. That little liquid in there is liquid butane. And as you shake it around or it's bouncing around in solution, the molecules collide with each other and sometimes they hit the edge of the molecule and makes the molecules spin or rotate about their bonds. And as they spin, they'll feel those repulsions within the molecule and then they'll try and tweak or bend out of that shape and try and get into a more favorable shape. Okay, let's talk about another staggered conformation, so alternating with our groups, something called gauche. And I can't remember if that's German or French, but the word means awkward. Awkward. It's not anti, which is the most favorable one. It's a little awkward. It's still slightly stable, more than eclipse. That's a little awkward. Gauche. Okay, what we got? Let's see. We'll play the video, see if I can stop it. No, too soon. There, winner. Okay. If you look at the shape of the molecule, we'll orient it this way. Everything is staggered. We got, yep, the forward carbon has a methyl up. So it's forward group, then back group, forward group, then back group, forward group, and then back group. And it's alternating. That's not too bad. If you look at the distance between the groups, or the spokes of the helm of the ship, they're evenly spaced. This is nicely staggered. But it's also crowded. Oh, that's really good. I like visual things like that. I'm a visual learner. I see these hydrogens close to each other. Are they touching? No, they're not. But in space, they are closer to each other than they were when they were anti. And these electrons about the atoms can feel each other. They're repelling each other. So this is not a very good shape. But at least we're staggered. We at least have these bonding electrons alternating, getting good distance away from each other. And, you know, it's not ideal, but it's better. So gauche has intermediate energy, some stability. Sometimes these are favorable structures, depending on what else the molecule is made of. Cool. Let's draw this. A gauche conformation. So let's focus on the forward carbon. Forward carbon still has a methyl up and hydrogens left and right. Where my drawings go, hiding over here. See if we can keep all three on the screen. There's anti-conformation. Okay, so we said we're going to focus on the forward carbon. So forward carbon's a dot. The methyl group was way up high. Hydrogen bottom left, hydrogen bottom right. And then we had the back carbon. And then where was the methyl group on the back carbon? Was it up and to the left, I believe? Let's go check. Yep, the methyl group is on the upper left of the screen. Double check. Yeah, there's the back carbon. Rotate so I can see it. And so on the back carbon's here. Methyl group up and to the left. Another hydrogen on that back carbon pointing down here. And on that back carbon, there's a hydrogen pointing to the upper right. Rotate here so they overlap like a Newman's supposed to. Okay, so we said the methyl group was on the upper left, right, and so I begin the bond on the circle to represent, hey, this is a group on the back carbon, CH3. There's another hydrogen over here, another one down here, and this you can label as staggered. You get partial credit because this one up here is also staggered. The anti-conformation has alternating groups. So there's this one, but between these two shapes, who is more stable? Well, find out where the biggest groups are first. They're the ones that are going to be the most crowding. And they're together here. They're kind of crowded. Not as bad as these two methyl groups. Like, yikes. It's crowded. Very, a lot of electronic repulsion there. This is high energy. How'd you get here? Because we forced it into this shape. You let go, they're going to twang, repel each other, and try and go. Well, they'll start by going gauche. That's the name of this staggered conformation. So at least the methyl groups are a little more, has a little less crowding. They're farther apart. But it'd be best to get into this anti-conformation. They're even farther apart, greatest distance. Biggest groups have the most room. That's more stable. This is a lower energy, actually the lowest energy conformation. The most stable. Should say most. There we go. Okay, that's essentially what we needed to do today. We got the main ideas, got some definitions down. We got some ways of analyzing shapes, ways of doing conformational analysis. All right. I stopped screen sharing. Sorry about that. I want to go over here. Anything else on here? Oh, minor point. That was conformational analysis of butane. And actually, there's something else we can do with butane, a deeper analysis we'll get to in a second. But what if you don't have butane? What if you have a more branched structure? First of all, what is the name of this molecule? Oh boy. So yeah, so you're gonna have to be able to do this from time to time. What you have to do is remember, oh, I got the little, looks like the ship's helm of the helm of a ship here, the steering wheel, steers a rudder. Where they intersect in the middle, that's the forward carbon. The circle is the back carbon. So maybe I'll start here and say, hey, this looks like there's carbon 1. The dot is carbon 2. The back carbon circle is carbon 3. And then the longest chain would be 4 and 5. So right here is the parent chain. 5 carbons, that's pentane. And if you number to get to the first branch as quickly as you can, off of the dot, which is also carbon 2, the forward carbon is carbon 2, there's a methyl branch. Yeah, the name of this molecule is 2-methylpentane. Okay, and then the question for you is this an anti-conformation? Well, look at your two biggest groups. With respect to the dot and circle, let's take away all that marking so it's a little more clear. Okay, so on the dot and circle, well, on the dot, where are the biggest groups? Hydrogen, no. Methyl or a methyl? Methyl. Darn it, it's a tie. These two are of equal size on the forward carbon. On the back carbon, we have an H. Yep, here's where the connection to the back carbon is. Back carbon, here's an H. This line stops on the circle, so that's the connection to the back carbon. It's an ethyl group, a 2-carbon branch. I know that's part of the parent, but as you analyze a Newman, you say with respect to the forward and back carbons, what are the groups? The back carbon has an ethyl group on it. That's the biggest group in the whole Newman projection. And now you could say, hey, this methyl is anti to the ethyl group, but that's not what's determining the energy of the shape. How stable is it? The most important interaction is this methyl's crowding the ethyl. That's a gauche interaction. This is a gauche conformation. Yeah, I know most of us want to say, but it's also anti. Anti is stabilizing it, but what's messing it up? What's tweaking this molecule, making it unhappy? It's crowded over here. Not so good. And so that's the most important feature. So we properly label this as a gauche conformation. Last thing we're going to do here, dealing with Newman projections, I might ask you to draw an energy diagram. So you need to review what an energy diagram is. I got a separate video for that. And what we're going to do is rotate, just like in this animation, rotate about the carbon, the carbon 2, carbon 3 bond. That's the bond we've been drawing down. And I want you to include some Newman projections. Okay, so let's see what we're doing. Let's go back to the animation. And actually, let's show you full screen. And we actually already have a graph. Kind of cool. Okay, so let's play it. There we go. We'll start here. And you can see that, again, keep moving the mouse around, keep playing up the screen. Okay, so we're up here, high on the graph, meaning, well, it doesn't say so. Oh, here we go. If you press on the screen, that's cool. This is 5.7 kilocalories per mole of energy, of rotational steric energy. Crowding energy is sterics. And then down here is an energy minimum, low valley, a low point, that's a 0 kilocalories per mole. If I click on it, it puts it in that shape. The what shape? The anti-shape, anti-conformation. Here's another energy minimum. Go here, please. There we go. What shape is that? It's hard to see what shape it is from the side, but if you put it in a Newman, so we're looking down the carbon 2-3 bond, then you can see it's staggered. The groups are alternating, but the methyl groups are side by side. That's a gauche conformation. And there's another gauche conformation over here. That's fun. I like it. And then these top ones, that's energy maximum. Ooh, max out. What's going on here? This is an eclipse conformation, but look where the two methyl groups are. They're not overlapping each other. We have a methyl overlapping, eclipsing a hydrogen, and another methyl hydrogen eclipsing interaction here. So those are bad, just not as bad as when the methyls collide with each other. That's cool. So kind of take a look at the graph. The graph is plotting the energy. Nice. And so what's the pattern, right? So if you have to memorize this, that's a horrible thing to say. You need to understand this. And if you understand it, you could draw it then. So it begins by understanding what a Newman projection is. And then if you draw, let's say you start with the eclipse, which is the shape this is in, the worst eclipse conformation because there's more than one. You got the methyls eclipsing, not the methyl hydrogens eclipsing. Let's get the methyls eclipsing. And then as we hold it in the Newman projection, think about steering the ship 360 degrees. Grab the, I think the back one's rotating, is that right? Yeah, the back carbon's rotating, just like the helm of a ship. And we can draw those conformations, and they're drawn for us down below. So right here, down the bottom left, we have the eclipse, properly labeled there. And then it looks like the back carbon is staying the same in these Newmans, right? So on the circle, pointing up is methyl. On the circle, it's pointing up as methyl. On the circle, pointing up as methyl. Yeah, the back carbon's staying the same. So let's give this a 180 spin, so the back carbon will stay pointing up. And if I play the video, the forward carbon should spin. Yes, it does. Cool. Nice. Okay, so we are in the right spot. Let's go here. Okay, just do this all day. Sorry. I'll have to give you the link so you can play around with this too. All right, so we're starting in this eclipse conformation. Methyls are both up. Start, 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 then stop. A little late. I stopped a little late, but we're pretty close to the staggered gauche, right? The dot here on this Newman projection is supposed to represent the methyl. Don't draw this on the exam, right? Because this looks weird. We haven't talked about what a dot represents. This is just someone's shortcut. And this isn't good enough for me. I would say, wait, the end of this line, that looks like a skeletal drawing. There should be a methyl here. End of this line's methyl, a methyl here, a methyl here. I don't know what this filled in dot is. What the heck is this? Okay, so don't draw this on the exam. Be careful of leaving your bonds dangling like this. If you don't put an atom there, we assume it's carbon. And the carbon bonds 4 times, so it's a CH3 group. Okay, enough about me complaining about these drawings. Where are we at? We just drew this shape here. And we're supposed to be at the bottom here where it's at an energy minimum, not as low as the best anti, it's gauche. It's staggered. And if you go a little farther, this methyl's going to eclipse this hydrogen. And I don't think I can get there. Oh, I did. Not too bad. It's off. Close enough. We missed the maximum. But we're supposed to be drawing this. The forward carbon's methyl group is on the bottom right. That carbon's always pointing up. That's what this back carbon's hydrogen or methyl group is. So keep going. Missed it, but we're supposed to get through the anti-opposite big groups. Energy minimum here. Right? So if I ask you on the exam to draw this, you don't get to use this computer program. Draw the Newman. And then when you draw the biggest group's anti, know you're going to be in a valley on your energy diagram. Keep going. I missed the other eclipse. It's right here, pretty close to the top of the peak. Go a little further to the next gauche. We're over here. It's supposed to be in the valley. It's staggered. Big groups are together. That's where this bottom of the valley is not as low as this one. Even though it's staggered, that's why it's a valley. The big groups are together. So this point where the 2 big groups are together is crowding more than when the biggest groups are apart. And finally, last place is the eclipse. Way off the screen here, highest energy, because the biggest groups are crowding each other. Okay, that's all for now. I'll see you later.